Hi, I'm Ben-Yaakov. This presentation is entitled PFC Front End of Pulsive. There is a lot of buzz today about a so-called revolutionary controller of Pulsive company, but there's really very little engineering information that explains what is really this product. There are some statements like, for example, novel flyback-based switching architecture offers efficient alternative to LLC converter. Well, not really. And then we have some other statement. So the objective of this video is to explain the technology offered by Pulsive. In the presentation, I'm sort of trying to screen out the noise and unsupported claims that the media is feeding us about this Pulsive technology. For example, Pulsive itself says the world's most advanced power electronic technology. Well, I'm not sure about that. And then we have explanation like this. This is from this electronic design article saying that it performs high efficient AC to DC conversion using an application-specific MCU to control the two switches. Here are two switches, and the switches alternately charge and discharge a small capacitor, this is this one, according to an algorithm that smooths inrush and output current. Well, that's not exactly it, and this is not exactly the configuration that is being used, and it is not smoothing the output current. So I did a lot of digging because the company is saying that they have a lot of patents, but they do not give out the number of patents anywhere. So I had to go and to try to understand what is this technology all about, and eventually I traced this patent, which seemed to be the major one of the technology. So this is a US patent. I guess there are some in other countries I didn't bother to find out. And here are the basic configuration they are talking about. Here is one which is sort of resembles the one that I've showed earlier, but as it turns out, even in the patent app itself, they're saying that the better or preferred solution or embodiment of this invention will be using a buck converter. So it's not just a simple switch, which everybody understands is very bad. Because if you have a voltage here coming from the input, rectified input, and then you charge this capacitor, you have sort of a switched capacitor converter, which may not be that efficient. And indeed, they are actually using a buck converter, shown here. Okay, so this is the basic circuit, and now let's try to understand how it works and what does it really offer. So here's the system, and this is, by the way, the evaluation board that they have. There is a line filter, there is an active bridge, which is optional. Of course, you can use just diodes, and this is the unit that they're actually selling. And there is a hold-up circuit. Since the unit itself, here this PFC, does not have a large capacitor within it, and therefore you do need a hold-up capacitor in case you need hold-up for the system. However, the main point is that this circuit has to work with an external DC to DC converter, okay? And I'll explain it later on, and I'll show that this is a sole point which is not clear as yet how it's going to be actually built and how the whole system is going to operate. So let's understand what is the circuitry all about, and this is the basic switcher that they have for the power factor correction. I'd say so-called power factor correction. We have the line, a filter, a common mode filter, and then some capacitor to ground. And then we have a rectifier, and then this is actually what the company is selling. This is a dedicated MCU program for the operation of this circuit, and it operates a switch. And here is the switch, which needs a high side drive. This is a high side drive. So here is the switch, and then we have the buck converter, and then we have the capacitor we talked about, and this is the other switch. So this is one switch, this is the other switch, but this one operates in PWM way, actually activating a buck converter. So now probing into the actual switcher here, we see the high side drive. This is a bootstrap supply here, a switcher, a transistor, a power transistor, the buck converter, the capacitor, and then the other switch, which is a diode. Output is coming from here. So how does this thing work? Well, let's have a look now at the cycle here, or half a cycle of the mains. At the beginning, we have, of course, the voltage building up after the rectifier. This is the voltage here. There's no bus capacitor here, okay? So this is just the output, the rectified output of the line. And the buck converter is operating, charging this capacitor. And this capacitor, here this capacitor is being charged. At this time, we see actually the input voltage. Now, once we reach this point, the buck converter stops operating, and then the capacitor is actually clamped to this line through this diode. Now the voltage at the input coming from the line is now lower, so therefore we are going to see the capacitor voltage, and then we have the capacitor being actually discharged. So this is the capacitor being discharged, and we see it, of course, the line here, the high voltage DC line. Now shown here is a resistive load. This is a resistor, and this is the problem of the circuit, and I'll discuss this in a minute. Let me just point out that the waveform that we see really resembles the so-called valley field rectifier. A regular rectifier with a capacitor filter will have a voltage looks like this, capacitor being charged and discharged, and the input current is pulsating like this. Now with a more clever connection, 2 diodes and 2 capacitors, these are fairly large capacitors though, you can get this operation. I'm not going into it because this is not the subject matter of this presentation. And you get it here with the lower ripple. This is the valley field here. The input current is not that great, okay? The harmonics are high, and probably it will not pass the norm for line harmonic standard. But this waveform sort of resembles what we get in the proposed, or this Pulsive technology. Now the main problem is that what we are getting is this waveform, and we need now a DC to DC converter to produce a DC voltage to a load. Now this DC now is getting this input, which is not that different from just rectifying the line. I mean, except for this filling here, which makes the ripple a little bit lower. This is just the regular rectified voltage. So this DC, which they are saying that it's going to be because it has not been demonstrated, it's going to be a flyback up to, they're saying 250 watts. Well, we're going to see that, I hope. Then this actually has to act like a power factor correction, because you have to control the current coming in. A regular DC to DC with a low voltage will require a very high current at the input, because the power is supposed to be kept constant, and once the voltage goes down, the current will go up. So this is now be reflected into the input and will corrupt the current at the input, and of course distortion will be very high. So the key to the operation of this whole idea is this DC-DC and how it's going to be implemented. There is no hint on that as yet. Well, hopefully they are working on it, or perhaps they have a solution that will show us. They are talking about a flyback, but they are also saying that this technology is also compatible with very high power, like 1 kilowatt. I don't see how you can do it with a flyback, probably it's another circuit, but still you'll have to have some sort of, I'd say, power factor correction in this circuit, because you have to make sure that you are not corrupting the input current via this unit by the DC-DC converter. So here are some waveforms that are showing for the evaluation board. This is about 150, I guess, watt. What we see here is the voltage, the high voltage that is generated, the DC voltage after rectification. You see here the valley. This is the valley here, which is about 50 volt, and the peak is 145 volt. This is the voltage on the capacitor, the holding capacitor, and this is the input current. Well, I don't know whether it's passing the norm of power factor correction or not, but it's not important, because I think that this has been taken with the resistive load. So the question is, what is going to happen if you have a DC-DC converter following this unit? Because with resistive load, this is really useless. So this is the question, and I have here actually a zoom of the circuit. Again, we see here the line. This what will be fed to the DC-DC. This is the capacitor voltage, and again here we see the actual line current, and again this is for a resistive load. And then if you have a DC to DC, you have to make sure that it's not corrupting it, because a DC-DC might actually corrupt it, and the waveform will be with very high harmonic. So this is actually the main sole point of this circuit. The question of this external DC to DC, which the company has not shown as yet how to build it, how to realize it, and what of course will be the performance of this combined unit with this external DC to DC. They are showing some efficiency of the front end by itself. Well, as again, I think it's of little use, because what is important is the overall efficiency, and the efficiency of the DC-DC here may not be that high if you have this high swings of an input voltage. So we'll have to wait until we see what is the efficiency of the overall system, rather than just the switcher, which is just one part of the system. So what's the conclusion here? The Pulsive power factor correction device is a front-end circuit doing only part of the job. Evaluation of the value, competitivity, and economics of the proposed solution is really pending until the company will disclose the DC-DC details, that's talking about up to 1 kilowatt and up, and present the overall performance. So this brings me to the end of this presentation. I'd like to thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.